first and foremost, we are doing cryptography. And in cryptography, we often deal with large numbers. Basically, all over cryptography in like asymmetric algorithms, especially, we might see like thousands of bits for acceptable security. But in elliptic curve cryptography specifically, to achieve the traditional 128-bit security level, we need at least 556 bits. And in some constructions, we need to also use 384-bit numbers to represent elliptic curve points. This means that on most hardware, on CPUs, GPUs, FPGAs, we cannot really use built-in types that are usable by hardware directly to represent these numbers, which means that we need to basically represent them as slices of built-in types, as here on equation 1. For example, we have a number that consists of 8 32-bit digits, for limbs as we call them, A0, A1, and up to A7, which is how we represent 256-bit integer. And for like 384-bit integer, it's similar but with 12 limbs. And like throughout the talk, and in most like in our code base and most other code bases, the representation is always little endian. Little endian meaning that the first number is A0 is like the least significant part. So because hardware cannot manipulate such large numbers, we kind of need a software solution in order to do the things we want to do with these numbers. And basically, most computationally intensive operation we typically need to do in cryptography is multiplying numbers. There's a caveat that we need to multiply them modulo prime number, because most of arithmetic in cryptography is field arithmetic. But we'll kind of not talk about that today. I was going to, but it turned out that it would have been like too long of a talk. So there are some caveats, of course, when using, for example, Montgomery multiplier. We don't just multiply two numbers and then reduce modulo, but we like interweave multiplication and reduction, which makes it a bit more complicated. But for the purposes of this talk, we'll imagine that we mostly need to just multiply numbers and get a result as an integer, just to make things easier and like to have some focus to what we're doing. Yeah, as written here, multiplication is largely the dominating part of the computation when you're looking at the bottom level. Of course, when you see entities, you have multiplications by twiddle factors, which, except for special cases like in Niles talk, when we have basically bit shifts for twiddle factor multiplications, we will need to do like full multiplication by more or less random number. Or in elliptic curve operations, in elliptic curve arithmetic, most addition formulas, they also have a lot of multiplications. So at the lowest level, when you look at it, you see that multiplications dominate your compute. And here is just like formula we all know from school, the multiplication. By the way, do you see my cursor? Like, can I use it to point? Yeah. Oh, okay, perfect. So this is like just what we call a schoolbook multiplication throughout the slides. It's just a regular way to multiply numbers digit by digit, right? And if we just count it, the numbers, the number of operations needed, it's like n squared multiplication, because we need to multiply each digit by each digit, which is n squared pairs, and around 2n squared additions of limbs. And actually, in the 1960s, there was a question whether this was like the asymptotically optimal way of multiplying the numbers, like the two n-limb integers, and the answer is actually no. So turns out there is this like simple trick where you can just split the two numbers you want to multiply. Numbers A and B are split into A0, A1, B0, B1, and you can see equation 2. You can check that just by opening up the brackets that you get like the product you wanted. And if you look closely, you only need like 3 multiplications for to get the result. 3 n divided by 2 by n divided by 2 multipliers, instead of n by n multiplication, which, if you count it, saves you a quarter of multiplications if you do these 3 smaller products by our default algorithm. Okay, but that comes at some cost, and this cost is extra additions. So there is quite a bit of extra additions. We won't compute them directly, but it suffices to say, well, I mean, it's nice to note that this number is linear. So this number is some constant times n, so constant times n additions, with which we buy n squared divided by 2 multiplications, and n squared divided by 4 multiplications, and n squared divided by 2 additions. So it's obvious that at some point this trick will actually yield, at some point in terms of, for n large enough, this will yield less multiplications and less additions. And if you go one step further and apply this recursively, you can actually, it's not immediately obvious, but you can see that this yields subquadratic algorithm. So algorithm in which the number of both additions and multiplications of limbs, or digits, let's call them limbs, is subquadratic. It's actually n to some power that's less than 2. Okay, but in practice, it's actually better to, well, in most cases, as a rule of thumb, it's better to actually generalize this scheme in other way. It's better to split the numbers A and B not in 2 parts, but in 3, 4, or more parts, instead of doing this recursion. This will generally yield less operations counts, and this is known as Tom-Cook multiplication. I will not really detail what it does exactly, but yeah, basically, we will mostly talk about implementing Karatsuba, because Karatsuba kind of is a gateway method. It kind of trades multiplications for additions at the optimal like rate. And if your Karatsuba works faster than the default methods, you can just proceed to try Tom-Cook and other more advanced methods, like not advanced, but like asymptotically optimal methods. For example, like there are methods based on FFT that are almost linear, so that are n log n in complexity, but they only become viable on large, really huge sizes. So we'll not consider them. Okay, so GPU pressure. Okay. This will be very brief and very selective. So GPUs are parallel processors, and they are really good for like computing really parallelizable things, as we all know, and how they look internally is that they are composed of multiple dozens of streaming multiprocessors, which are kind of very similar like blocks of which are themselves internally subdivided into four like subdivisions, into four parts, which are basically the physical devices on which threads run. And threads don't run by themselves, but they run in so-called warps. So like warp, basically 32 threads, is like basically a unit of minimal unit that gets scheduled. So we don't schedule individual threads, but we schedule warps on streaming multiprocessors, and more precisely on their subdivisions. Not sure how it's called actually. That's called subdivisions. And you can see that there is a scheduler on top. So each of these subdivisions can issue one instruction to one warp in principle per clock cycle. So that's kind of the model of issuing instructions. And this instruction can go into different places. You can see in green our cores. There's also a lot of interesting details about memory of the GPUs, which we'll not touch in this talk. We're purely about compute here, and about how to use arithmetic, not about memory. So in32 and FP32 cores are, well, kind of for integers and floats respectively, but we'll detail that more. And this is a Turing. This is Turing multiprocessor, and in later, more recent architectures, more cores are added. It's more complicated, but this is like, I think 2019, basically. I might be wrong. So the two most interesting pipelines to us, or cores, it's FP core and in32 core. So these two, because they compute basically FP32 core computes integer products actually. Well, it's used for computing like float arithmetic, but it's also used to compute multiplications and fused multiply and adds on integers, interestingly enough. And in32 cores that I think have been developed mostly for like logic, initially they can also do, or I guess maybe for indexing as well. So indexing needs additions, like integer additions, so that's what they're good at. And there is like a table which for devices of compute capability starting from 7.0, so starting from Turing, not Turing actually, Volt, I think. It tells you like what's the throughput per clock cycle per streaming multiprocessor of these operations. So multiplications and multiply and add operations, they can be done 64 operations at a time, well, at a clock cycle per multiprocessor. And you can see how like here there are exactly 64 like cores, FP cores, which is why there are 64. There is a throughput of 64, but if you want a wide result, so if you want not just like if you do IMAD, you get only the last 32 bits of the result, and if you do like a wide multiplication, you get the whole result, and then your throughput falls by factor of 2. And additions, I had interestingly enough taking optionally 3 inputs and not just 2. They also come in a throughput of 64 because there are 64 physical like things here for N32. Okay, so that's extremely brief, idea of what the hardware looks like, and software. The code that you write for CUDA doesn't really is not that different from CPU code. It's kind of a variant of C++, which has like some extra special features that allow you to to schedule kernels, so-called, and use good APIs. But basically, when you write kernels, it compiles to a certain type of assembly language, which unfortunately is not editable. You cannot really write in it. Well, you can, but that's complicated, I think. I never tried, and it's not really well documented, unfortunately, as well. But it is device dependent. So for every architecture, for like compute capability, it's different. Your code can be compiled to just a different set of instructions because the instruction set changes, and so there is no like backwards compatibility and stuff. And these are like the main instructions that we will use for the multiplication. It's like IMAD and its versions, and IAD. So multiplication, fused multiplication, addition, and addition, right? And there's also an option to work with carries, to input carry and to output carry. And this is the example. The example of like a code that we compiled. It was at not really important what's the compute capability. It's just to show you how it looks like. There are you can see the names of methods followed by purple registers and blue predicate registers. So these predicates are 1-bit registers used for carries, and also you can see that they control the flow. Here it's P1. Like P1 basically tells you to not execute this operation. And this is like, by the way, one interesting difference between GPUs and CPUs, that you cannot really do branch prediction. You cannot really use the fact that some branches are rare. And if your code is, if your like predicated code inside like an if else, for example, block is not executed, not even by one branch, you still pay for it. And so that's one interesting detail that makes us try to avoid conditional code, basically, when writing programming for GPUs. Okay, so that's extremely brief introduction into what matters for this experiment. And so now let's jump to the results quickly. We tried to compare the baseline implementation that we took from Metro Labs, from Robert here, and he actually based it according to comments in the code on the zprice baseline done by Spark. I hope the attribution is correct. And we tried to just do one iteration of Karatsuba on top of that, and just invoke the default wide multiplier on the 3 products that we got. And basically that's the result. And we'll just now look at them, and we'll try to explain them and why it works the way it works. And now this talk becomes progressively speculative, because the low levels of CUDA are not very well documented, and some things I can just guess what actually happens. But yeah, please, for the people, numerous people in here who are better at this than me, please feel free to immediately like interrupt and correct, because I might be very wrong. But yeah, so what we got is basically that Karatsuba performs maybe like some 6% better on 256-bit. bits, some like I think 13% better in 384, which is expected because the larger the size, the larger the gap between Katsuba and just default method. And then we also tried to include this multiplier into Bicycle, which proved to be somewhat underwhelming because the performance boost for like MSM, don't look on sizes. Sizes are random. Doesn't really matter. It's just whatever benchmarks we had in Icicle. So it only improves MSM on like 2.5%, and then TT like some really 1.5% or something. So the performance improvement in like higher level methods is not really noticeable. It's like less noticeable than on the basic multiplication. And there's a host of reasons for that. We haven't improved reduction actually. We don't really have. I think we have memory bottleneck in NTT. Basically, it's not computationally bound, but memory bound. And MSM, it's complicated. So, like once you try to apply this to higher level methods, it gets complicated, and there are many other. There might be just different bottlenecks than compute, like memory. But yeah, that's the result, and let's just try to explain the results. So first of all, this is the the first thing I want to look at is what instructions are issued, right? Because we said that Katsuba saves us multiplications and adds additions, and we want to check that, right? So the scales are a little bit different, which is unfortunate on these plots, but you can see that 1 billion operations. Okay, the exact numbers are not really interesting. We're just interested in their fraction, like the how these numbers
ratio.
Yeah, ratio. So we can see that Katsuba basically exactly 1 billion operations, whereas the school book, I think it has like, I don't know what, 10% more. So yeah, we have a little bit less multiplications. We would expect to get a quarter less, which is not what we get. And the reason is because it's a battle with compiler. Compiler produces some, let's say, extra operations, which are pretty unclear to me. I'm not sure, maybe I misunderstand something, but it seems like it produces just suboptimal assembly. And there's much more additions. And I think just purely from looking at these figures, you would think that Katsuba should be slower. Basically because we save only a little bit of multiplications, but we add much more additions. And as you've seen, the throughputs are basically the same. Well, they're not the same. They are 2 times. Basically, all multiplications we're issuing are wide multiplications. So throughput 32 and additions throughput 64. But still, definitely, if you just add up the throughputs, the Katsuba should be worse. But now is the explanation of why. This is pipe utilization. So pipe utilization is a fraction of cycles where an instruction was issued to the pipeline. And we see that FMA pipeline is the one that's responsible for multiplications. So this is like FP32 thing. It is basically at like below 25% for both. But ALU, the one that issues additions, is almost 50% for Katsuba. So basically, if we go back to this picture, basically what this says to us that we're using up like FP cores quarter of time, and int cores like 50% of time. Like why quarter? It's actually it's kind of a technicality. I believe that they are actually fully utilized. Basically because there are two pipelines for architecture starting from Ampere. So basically, the FMA pipeline is two pipelines. One is FMA heavy, and the other is FMA light. For newer, more recent architectures, and basically we can only use FMA heavy for integer multiplication, and another 2x reduction in throughput just comes from the fact that we're using wide multiplications almost all the time, and that drops the throughput drops 2x for that as well. So yeah, I believe the FMA pipeline is basically as used as we can, and ALU is just 2 times more utilized for Kuba, and that's probably the secret. And if you look at basically, I have conclusions here. If you look at the issue like scheduler, so scheduler is much more used up in Karatsuba than in Schoolbook, but it is still only like half of the cycles that get an instruction from schedulers on average. So basically, I would like to conclude with this idea that we probably still are underutilizing the ALU pipeline by basically 50%. We can maybe add more additions without really changing the throughput, because both scheduler and ALU pipeline are underused still. And so that kind of tells us that we might try to, especially for 384-bit multiplier, because these pictures are for 256-bit. For 384, we get actually much less performance from ALU because we get proportionally more multiplications. So yeah, basically, we still have like additions to add in trading them for multipliers. And yeah, I guess one caveat to add is that we've now heard from Niall and Robert, who both talked about basically the commitment scheme that doesn't require us to use elliptic curves, and that means they can use a much smaller, much more efficient fields like Goldilocks, and it's now, as far as I know, pretty widely used in like ZK systems, the SARGs that use 32-bit or 64-bit representations that don't benefit from fast multiplication. But I would really be curious to hear what you think when it comes to larger fields, whether or not this makes sense. My explanations especially, I mean, maybe you have a better one. I can later show the NVIDIA Systems profile, which is interesting.